So we started last time with a discretization of the diffusion term. And we have developed what we call the control volume analysis. Because to summarize, if you remember, we considered a control volume of dimension delta x, delta y, delta z, and we applied the conservation law on this control volume in order to get the equation of diffusion. And we said that this equation can be applied for conduction. In case of heat equation, we can have the variable of concentration to solve for the concentration profile, etc. So whenever you take a control volume and you do the analysis of fluxes getting in and out, and you write the conservation equation, this is called the control volume approach. And we developed this approach for 2D case. And of course, if you have 1D problem, it's same concept, but much simpler. And you have just to take into consideration, let's say you have heat conduction in 1D, then you have just to take fluxes along X, okay? So this is about the control volume method, and we derived together the expression of all of these coefficients in order to come up with a numerical equation replacing the differential equation. Now, if you remember, when we considered the coefficient, we had to take into account the diffusivity coefficient at phases. We gave an example in class. We said that if K is constant, let's say we are dealing with heat balance, and you have the conductivity is constant, then of course all of these parameters, K east equal to K west equal to K north and south. So this will simplify a lot the analysis. But what if it's not the case? What if the conductivity K, let's say, is function of temperature, for example? Then I can, since I will solve for the temperature in cells, so I will solve for Tp, for T west, for T east, south and north values, etc. I can try to interpolate the value of K at the phases. So let's say K is function of temperature, and I only know temperatures on at points. When I solve for my control volume, in my control volume method, I consider that the temperature is calculated at points, okay, at the center of my cells. So if I want to compute, let's say, the conductivity K at the phase, I should do a certain interpolation. So I can calculate, I have K function of temperature. I can calculate conductivity at P. I can calculate conductivity at E. But at the east phase, I don't have a value for K. I want to interpolate. Now you can tell me maybe I can assume linear profile, for example. No, I assume that conductivity is varying in a linear way between P and D, and I compute the value of K at the phase. This is a possibility, but it's not the best choice. Why? Because I try as much as possible, if you want, to keep the physics. So when I deal with the heat equation, okay, I have that the flux, conductive flux here, okay, that is getting out, let's say, from this control volume, is equal to the one that is getting inside the adjacent control volume. So I can interpolate K in a more physical way by saying that the value of K at the interface should be in a way that the flux, the conductive flux between point P and the east face is equal to the conductive flux between the east face and point E. So in this way, I will consider the physics of my problem, that the conduction heat flux across the face getting in and out is the same. And then I will get a better interpolation of K. Okay? So here we'll see together several possibilities to compute K, and the best one is the one taking into consideration the continuity of the conductive flux. So between the conductive flux between P and the east face is equal to the conductive flux between the east face and point E. So a first approach, as we mentioned together, is the linear variation. So I say I can assume linear variation of conductivity in case of thermal application. As we mentioned in class, for a general application of diffusivity, we use this coefficient symbol. So we can say that if we want to apply linear variation, we can consider a certain coefficient GE and say that tau at east face is equal to 1 minus GE times the conductivity or diffusivity coefficient at P plus the coefficient times conductivity at E. Now, how to define this coefficient is very simple. If you are doing a linear approach, then if you look at this figure here, you know that the distance between point P and the east, this one, is equal to half of delta x. So this is delta xp over 2. Okay. And the distance between this the east face and point E is delta xe over 2. And if you apply a linear interpolation between the 2 points, okay, you can say that I can define the coefficient at the east face as so if you want to apply the linear interpolation, you can say that if delta xp is 0, so if the east face is very close to point P, okay, then what will happen? What will happen is that the conductivity at the east face will be equal to the conductivity at point P. So this is why we say that we can consider then, if I define, let's say, a coefficient here to be 1 minus delta xp over 2. So the closer I am to the point، يعني كل ما delta xp over 2 بتصير أصغر، كل ما بتقرب ال diffusivity at E من diffusivity at P. So I multiply 1 minus delta xp over 2. Sorry, not 1 minus، يعني the whole length here. يعني أنتوا you have that. You should consider, if you want, what is this distance, يعني the distance, the total distance minus this one. So let me, إذا بدكم هن حكينا كفوليوم، فينا ناخدها كفوليوم. why? Can take it as volume because في proportionality، يعني عندكم ال thickness. Let me take the thickness here, okay? The thickness here is the same. T, you have same thickness, and we are working in 2D, no variation in thickness, okay? And for all of these faces, you have same delta y. Delta y is the same. ما بيبقى إلا delta x is varying, okay? So you only have that delta x is varying. So you can define our function of delta x. هلا بنرجع نحولها أنا وياكم لدلتا x. Our function of volume. So if you define G at east as volume of the control volume centered at P over the volume centered at P plus volume centered at east, شو بيطلع لنا ساعتها? If you want to express a function of delta x, you know that the volume here of this control volume centered at P, VP, can be defined as following. هو delta x تبع السيل P times thickness times delta y, okay? And now, if you divide VP, by VP plus V east, you get that it's over delta xp times t times delta y, okay, plus delta x of the cell centered على point E، يعني هنسميها delta x E، okay, times t times delta y. So because you have same thickness and same delta y, then you can say that the coefficient GE اللي هو linear coefficient اللي هنستعمله is equal to delta xp over delta xp plus delta xe, okay? And now if you divide over 2 everywhere, nothing will change. يعني if I divide here delta, if I do delta xp over 2, and here delta xp over 2 plus delta xe over 2, what do I get? I get the following coefficient اللي هو this distance. So I will clear to write again, okay? Delta xp over 2 هي head distance. This is delta xp over 2. And this is delta xe over 2. As you can see, the summation of these two هي equal the distance between centers P and E. هي equal delta x of E. Okay, so if you apply the linear variation, you get that the diffusivity coefficient على east هي equal to نحن we said GE is defined as delta xp over 2 over the summation of these two اللي هي distance between centers of control volumes, يعني over delta xp. And we will see together why this makes sense. كل ما صغرت delta xp compared to delta xe، يعني east, okay, this point will be closer. So if delta xp is very small, okay, this point will be closer to this one, and then should be affected more by its diffusivity value, okay? So هون عنا this is 1 minus GE بتطلع delta 1 minus delta xp over 2 divided by delta xe okay. So what do you get then? If you do same denominator بيطلع هون عندكم delta xe minus delta xp over 2 يلي هي delta x east over 2. يعني in summary هيدا الترم بيطلع delta x east over 2 and this term will be delta xp over 2. And now the extreme cases is a delta xp is 0، يعني east face يعني على point P شو بيصير ساعتها؟ This coefficient will be 0, this coefficient will be 1. ساعتها conductivity at east will be equal to the conductivity at or diffusivity coefficient at P. And if you have the other extreme case انه تكون east face very close to point E، ساعتها delta xp هي بتصير الdominant. Okay, then this coefficient will be 0 and this coefficient will be 1. And if for any case in between, يعني wherever you put your east face between the control volumes, as we said, هيدا is a non-uniform grid. You remember we said that we can have uniform grid and non-uniform grids. So if we have uniform grids, ما عندنا كل هيدا البروبلم. You can directly say, if I want to take linear interpolation, أصلا you can find it directly from the formula. إذا the east face is at the middle, يعني حيطلع delta x p over 2 هتكون equal لدلتا x e over 2. فحيكون exactly إنه الcoefficient على east face هي 0.5. الcoefficient على p plus 0.5 الconductivity coefficient على e. Okay, but in case you have any other point, يعني in case you have non-uniform grids, for non-uniform grids you can have change in cell size, then this will be the linear interpolation. بيكون في coefficient that will depend on how much the east face is close to p relative to its position from E. كل ما كانت أقرب على P هتتأثر أكثر بالconductivity أو بالdiffusivity of P. Okay, so this is the linear variation interpolation. هلا in general it's not a bad interpolation, but it's not the best choice as I told you because it will not take into consideration the physics. It's better to include the physics in the interpolation. What do we mean by including the physics? Why I don't say that I have that the conductivity flux between P and the east face is equal to the conductivity flux between point E and the east face. Okay, this will be much more physical. And this will give me a conductivity coefficient at the east face that is representing the physics of conduction. So how to do this now? This is another approach to compute the conductivity at the east face. I will say that the linear approach will lead to incorrect implications in some cases and cannot handle, for example, sudden changes in conductivity that may occur in composite materials. And if I have sudden change in conductivity, linear approach will not work well. This is why we tend to develop a more physical computation of the conductivity at east. And we say that we'll focus then our attention on the heat conduction equation in a way that the flux that we are interested in coming into P and coming into the east face and getting out of the east face is the same. So if we take this idea to find the equivalent conductivity or diffusivity, if we are taking the general case at the east face, then all we have to say is to apply the continuity of the conduction heat flux. Okay, so because our main goal here is to have a good representation of the conductive flux through the interface. So let us say this interface will be subjected to a conductive flux coming from P towards E. And we have a conductive flux from east face towards big E. And let us write the expressions of the conductive flux coming in and out from this face. So you have, first, if I take this one, this flux, what is its expression? It's minus K delta T over delta X, okay? So here, if we are dealing with a heat equation, the conductive flux at the east face coming from point P, if you want, towards the east face, can be written as, because we have minus Kp delta T over delta X, okay? And delta T over delta X is T, you know that in general, نحن حولناها هون لنيوميريكال بس هي أصلاً الconductivity coefficient هو minus K del T by del X. But since we are doing numerical interpolation, we can approximate the gradient of temperature by delta T over delta X. Delta T over delta X will be the temperature at east minus the temperature at point P over the distance between them. So it's minus K, temperature at east face, minus the temperature at point P over delta of x. Okay, هلا if you take the minus inside بتصير kp times tp minus t east over delta x, which is x east minus x of p. And x east minus x of p, you can replace it by delta xp over p. So this is the first expression of your conductive heat flux. And since it's equal to the flux going from the east face towards point E, so you can write it in another way. You can say that this flux can be written as K at point E times TE at east face minus TE at the midpoint of the control volume over the difference between XE and X of the east face. Okay? And this is delta X east over 2.
دكتور
نعم؟
دكتور
Yes.
نحن على اساس عم نحط كي بي او كي اي
ايه على اساس انه نحن ما بنعرف الكوندكشن الا ببوينتس. اوكي، فانت بس تاخذ الفلكس when you take the flux from P to E, you will take conductivity at P. Okay, and when you take the flux from east face towards E, you will take the conductivity at E. هلا نحن شو هدفنا بالاخر؟ هدفنا نجرب نلاقي an approximation للكوندكتيفيتي على الايست فيس. هيدا هدفنا. اوكي، فتنجيب الكوندكتيفيتي على الايست فيس ليك شو فينا نعمل؟ هلا هول التو ايكويشنز اللي انت طلعتهم when you have a في mathematical rule بتقول انه اذا عندنا A over B equals to C over D. Okay, then we can say that this is equal to A plus C over B plus D. اوكي، يعني فينا نقول هلا نحن انه اذا بدنا we want to replace هيدا الفلكس بدل ما نقسمه من P to E بيرجع من الايست فيس to point big E، فينا نعتبره انه هو conductive flux واحد رايح from P towards E، حيقطع باي فيس؟ حيقطع بفيس E، صح؟ يعني فينا نقول انه هيدا الفلكس is equal to K at east اللي نحن بدنا نجيبها. اوكي، times temperature، يعني times temperature at point P minus temperature at point E over the whole distance from P to E. اوكي، يعني انت بتعتبر انه بستعمل K على الايست فيس لما اخذ الدلتا T over دلتا X بين points P و E، ولما اخذ between points P والفيس E باخذ ساعتها الكوندكتيفيتي at P. and when I take the flux from the east face to big point E ساعتها باخذ الكوندكتيفيتي at P. and this will help you. هيدي الايكواليتي هي حتعطيك الفاليو لكي equivalent. اوكي، لانه هول 3 fluxes are equal، هول قد بعض. يعني هون if you do the summation of numerator والdenominator بيطلع لك انه KE times TP minus TE over this whole distance يلي هي delta XP over 2 plus delta XC over 2 which is delta X east. Okay, you get that this is equal to KP times TP minus TE plus KE times TE minus T big E over, if you sum these two إذا بتجمع هول الاثنين x of e بتروح. Okay, so you get then xe minus x. Okay, and this will help you into getting an expression for this conductivity coefficient at the east face. Okay. It
دكتور
is
أنا هاي الإخوان ماجستير بكون بعرف من محلات.
Sorry, can you repeat? The voice is lagging a little bit.
أوكي هيدي البوا ماجستير بيج إي أنا بكون بعرف وين محلها.
Yes, yes, of course. بيكون أنا عندي بيكونوا هن عاطيني الجريد how the grid is changing. Okay. يعني هن بيقولوا لي إنه مثلا إذا عندي non-uniform grid بيقولوا لي let's say the first element has delta x equal to let's say 1 centimeter and the other elements مثلا بيصيروا يكبروا الدلتا x تبعهم times 1.1. يعني let's say إذا بتتذكروا قلنا وقتها نحكي بالريفاينمنت انه ما فينا نعمل دغري sudden change in delta x. You remember قلنا انه عادة it's recommended for two cells that are close to each other انه let's say this is the first cell, let's say delta x1 delta x2 مثلا بتكون 1.1 times delta x1. يعني اذا عندي non-uniform grid بكون بعرف the size of each of my cells, so I know the distance between my points. I know كل الضل x معي هون وبيكون معي ال k let's say function of temperature. يعني أنا بقدر I can compute the value of k at different points so that I can deduce an expression for k على الانترفيس اللي أنا بدي إياه. يعني هلا you will see it in this slide, in next slide. So based on الايكواليتي للديفيوزيف للفلوكس للديفيوزيفيتي فلوكس. اوكي نحن كتبناه in two ways هيدا الديفيوزيفيتي فلوكس and once you write it in two ways يعني هون كل اللي عملوه انه اخذوا k لتحت. يعني طلعوا هون انتوا عندكم k times. اوكي so بدل ما يحطوها فوق حطوا هيدي over k. That's it. So they divided here by Kp, they divided here by Ke. بعدها نفس الإكسبريشن يعني بس غيروا محل ال K. You know why they did this? غيروا محل ال K بس يعملوا ال addition A plus B over C plus D. ال TE will cancel out in this case. يعني when you do the addition بيطلع لكم in the numerator TP minus TE over in the denominator you get XE X east minus XP over the conductivity at point B plus X east minus X big E minus X على الفيس over KE. هلا شو بيصير when you equate the two expressions للheat flux? Okay, when you say they are equal, you will see that TP minus TE will cancel out. فبيطلع لكم that the equivalent conductivity coefficient على east face over delta X east اللي هي distance from P to E is equal to this distance over Kp plus this distance over Ke. يعني you were able to interpolate the coefficient at east in a way that is more physical, that will take into consideration the conservation of flux. The one that is coming from here is getting out. Okay, على الايست فيس. يعني اللي بيجي towards الايست فيس هيطلع من الايست فيس على ثاني control volume. So this will give you the following interpolation. If you rearrange your terms, okay, so by rearranging our terms, we get the following expression for Ke. You have 1 over Ke. إذا بتلاحظوا هون, okay, this is the equation we got by just dividing all terms by Xe minus Xp اللي هي delta X east. Okay, you can come up with an equation of K east function of KP و KE. Okay, هلا if the grid is uniform, this is the easiest case. If the grid is uniform بصير هيدا الريشيو F east اللي هو XE minus X small e over XE minus XP بصير equal 0.5. And if it's equal to 0.5, okay, then you replace here 1 minus FE by 0.5 and FE by 0.5. And you get then what we call the harmonic interpolation of the diffusivity. يعني أنا ما عم بعمل linear interpolation. I'm taking an interpolation based on the continuity of the heat flux. So I can compute then K at east face function of K at P and K at E. So if you have uniform grid, you can say that K at east face is 2 KP KE over KP plus KE. If you have non-uniform grid, it's not a problem. All you have to do is to أكيد بتكونوا قادرين تعملوا calculation. يعني مثل ما قلت لكم, if the grade is not uniform, you know how the cell size is changing, and then you can define a certain coefficient factor which represent this distance over this one. Okay, يعني it's a weight factor مثل بالlinear variation if you want. Okay, so and as usual كل ما الفيس تقرب على البوينت أكيد حتتأثر بالconductivity تبعها أكثر. So here this is the same idea as we did for the linear interpolation. The closer I am to the point, the face will be affected more by its diffusivity. Okay, so this is the general expression for non-uniform grid. And in case the grid is uniform, all you have to do is to replace your weight factor by 0.5. You get the following expression. And as you can see, بالlinear إذا أنا عندي uniform grid, linear interpolation بتعطيني arithmetic mean. لأنه if I apply linear variation بيطلع لي K east for uniform grid equal to KP plus KE over 2. بينما if I take the physics into account that the conductivity flux is the same coming in and out, then I get that this is what we call the harmonic mean, and it's more representative. So this method is more recommended for interpolation of the interface diffusivity, and it will represent less problems in numerical computation. Okay? Any question on how we determine the interface diffusivity for non-uniform grids?
دكتور البيج بوينت هي حيلا بوينت على الايست سايد ما هيك؟
البيج بوينت هو center of the adjacent cell. يعني انت عندك البوينت B عنده control volume. This control volume is surrounded by other control volumes. في one control volume at west, one control volume at east. هلا هون مثلا فرجونا non-uniform grid. هلا اكيد هون شوي exaggerated يعني. اوكي, نحن عاده مثل ما قلنا الترانزيشن بالسايز ما بتكون كثير كبيره ولا it's not good. يعني if you do such big transition in size you will have numerical problems. فانت البوينت E هو center of the phase of the control volume at the east of the control volume centered at P. والبيج W هي the center of the control volume at west of P. Okay?
Okay.
If you go back to this figure here, showing you all control volumes, شايف هون ال P هو center of the cell that I am working on. The W who center of the cell at west of my cell. E is the center of cell at east of my point P. Okay? Well, you define then the faces, and this is the east face, this is the west face, etc. And in order to compute my coefficients, I need the diffusivity coefficient at east face, at west face, at north face, etc. Okay?
اوكي بس السال اللي بيكون على شمال الاي او على يعني على الويست او على الايست مش دول يكونوا قد بعض.
اكيد لا هلا هيدي الفيجر يونيفورم جريد، اوكي؟
ايه هيدي يونيفورم بس
مضبوط، هاي يونيفورم. اذا بدي فرجيك وحده نون يونيفورم، يعني ساعتها اذا ما كانت يونيفورم، هيدي الديستنس اللي هي دلتا اكس بي اوفر 2، اوكي، بتبطل ايكوال لهيدي الديستنس اللي هي دلتا اكس اي اوفر 2، ببطلوا قد بعض، بصير في ريليشن بيناتهم حسب كيف عم بتصير يعني انا قلت لكم بيعطوكم how the grid size is changing، اوكي، والسميشن تبع هول الاثنين هي equal to what we define as delta x e small e اللي هي الديستنس بين سنتر P والسنتر اوف سيل على الاي سي اللي هي e. اوكي
اوكي مش الحال.
any other question؟ طيب we'll do some we'll do some problems together to practice on this, don't worry about it, but please understand the physics beyond it لأنه as I told you يعني فينا بالإكزام يقولوا لكم first derive let's say the equation of تنقول heat problem, derive the equation of heat for the cell and then إذا بدكم use let's say harmonic interpolation to compute الK at east. يعني فيهم يسألوكم to derive a formula. You should understand the physics behind each formula and then how to apply it. Okay?
derivation يعني مثل ما عملنا on campus.
ايه derivation اللي عملناها on campus. نحن عملنا the general derivation على 2D. إذا بعطيكم 1D يعني it's much easier صح؟ نفس الكونسبت بس بيصير فيه only variation in one direction instead of two. يعني that's it. You should know the idea. إنه I get a control volume. I consider the fluxes coming in. I consider fluxes coming out. I write my equation. هلا if you remember نحن أخذنا هون الكيس of pure diffusion. هلا حنرجع نعيد الاناليسيس إذا في convection و diffusion تترجعوا تتذكروا كل الستابس. أوكي؟
اوكي.
طيب هلا أهين شيء أكيد إذا الكوندكتيفيتي أو الديفيوزيفيتي constant يعني كل هيدا الشغل ما له لزوم بتكون K the same everywhere. Okay, so we are done with the computation of K. Now we'll move to boundary conditions. The boundary conditions are very, very important in CFD. What we did together, we derived, if you remember, we will transform a differential equation into a numerical equation, صح؟ وحنكتب لكل control volume a numerical equation. فإذا برجع to this slide, what we will do for each control volume حنكتب conservation equation, okay? And once we are done, ما نحن كتبنا coefficients. هول coefficients AP phi P plus coefficient AE phi E plus AW phi W plus A north phi north plus AS phi S equal to a certain source term. اتفقنا؟